Hello, George Romanic here. In today's video, we will tackle an advanced topic in atmospheric sciences, namely in the field of dynamical meteorology. And that is to reinforce our conclusion from the previous video that the atmosphere at large scales in mid-latitudes is in hydrostatic equilibrium in vertical direction, of course. In previous video, we used scaling or scale analysis of the vertical momentum equation for large-scale motions in mid-latitudes to demonstrate that at those scales, atmosphere is in hydrostatic equilibrium. And that is good conclusion at the beginners to intermediate levels. If we want to be more advanced, we need to generalize this conclusion. Namely, hydrostatic equilibrium holds for static fluid at rest. In atmosphere, we have winds. And those winds depend exclusively on horizontal gradients of pressure. So, in the presence of winds, we really need to also demonstrate that those horizontal pressure gradients are in hydrostatic equilibrium with horizontal fluctuations or horizontal gradients of air density field. If we also demonstrate that, then our conclusion from previous video is reinforced. And that will be topic today. To tackle this topic, I will also introduce a new concept that we will from time to time use in atmospheric sciences in this channel, and that's decomposition of a field variable into base state and fluctuation or deviation or perturbation from that base state. It's a very useful concept that can help us to solve many problems in this field. So let's tackle this problem. I would say that good starting position in this video is to see what we have if we apply simple scaling analysis for the vertical momentum equation at synoptic scales in mid-latitudes. We see that the vertical component of the pressure gradient force and gravity are the same order of magnitude and much larger than the other components in this equation. So if we adopt this argument, then we can immediately see that we retrieve hydrostatic equilibrium, namely, and I even explicitly derived this equation in one of the previous videos. So first, let's look what this equation tells us. This equation tells us that pressure at any point is equal to the weight of a unit cross-section column of air above that point. Let's sketch that. Here we have a surface of the Earth, and let's say I'm at this height, Z, above surface. Pressure at this height is the weight of air in this column from height Z all the way to the end of the atmosphere. At the base of this unit cross-section, we will have pressure, and that pressure will depend on height Z, and we will also have density that will depend on height Z. And we know that both pressure and density approximately exponentially decrease with the height. But now, let's say there is wind blowing like this. And you have to now imagine that these are at synoptic scales. That means, let's take another point over here, the same height Z above the surface, and the pressure again is the weight of air column with unit cross section above this height. Here we also have pressure P that is function of Z and density ρ that is function of Z. Now when we have this schematic and we have this equation, this is the argument that we want to pursue. This equation holds for static fluid. Here we have wind, and we want to show that in this case when we have wind, atmosphere at synoptic scales is still in hydrostatic equilibrium. This wind is only coupled to these horizontal differences of pressure. So we need to demonstrate that these horizontal fluctuations of pressure that cause this wind are in hydrostatic equilibrium with horizontal fluctuations of density field. Because if that is not the case, then atmosphere at synoptic scales is not necessarily in hydrostatic equilibrium. To do this, we shall define a standard pressure called P0, which is horizontally averaged pressure at given height, let's say this height Z. So I take this height from here to here, synoptic scale, and I average pressure along this height. That's my P0, standard pressure. And similarly, I will take standard density to be horizontal average of density at given height, let's say this height Z. These two quantities are defined so that P0 and ρ0 are in hydrostatic equilibrium. Namely, 1 over ρ0 dP0 dz is equal minus g. Why did I use normal derivative here and partial derivative here? Remember, P0 is horizontally averaged pressure on this height Z. So it cannot vary horizontally, it's horizontal average. It can only vary with height, and therefore it's a function of one variable, so I can use regular derivative. Whereas here, pressure can vary as a function of height as well as spatial coordinates. Now, with these definitions, we can write total pressure and density fields as that pressure at any point, and that means at a point x, y, z, and time t, is pressure P0 that is only function of height plus P prime, which we will call deviation from P0, which is function of x, y, z, and t. Let me just demonstrate. Let's say between these 2 points, pressure surface looks like this. It's a little bit inclined. Pressure is higher here than here, let's say. If I take spatial average, I will get this line, and that will be horizontal. That will be my P0. And that will only depend on height. If I go up, I will have different pressure surface. P prime, I pick this point over here, and this point has coordinates x, y, z in space, and we have time coordinate t. This over here is P prime. And you can see that P prime is different from P prime here, which has different coordinates, different from here that has different coordinates. So this is what this equation is telling us. And the same argument holds for density. The next thing that is important to recognize, and that can also be proven from measurements, is that P prime is much smaller than P0, and ρ prime is much smaller than ρ0. Which means, for example, ρ prime over ρ0 is much smaller than 1. Now, I hope you can see if P prime and ρ prime are 0, so let's write it maybe here. P prime, ρ prime equals 0, we have static atmospheres. In other words, there is no wind, there is no motion. Now, why is this important? This is important because in the pressure gradient force, we have expression 1 over rho, which means this expression 1 over rho is equal 1 over rho is rho naught plus rho prime, and that is further equal 1 over, if I factor out rho naught, I will get 1 plus rho prime over rho naught, and this is approximately equal, if we use Taylor series approximation, as rho naught to power minus 1, that's this, 1 minus rho prime over rho naught. Namely, 1 over 1 plus something small is in Taylor series as 1 minus that small. So 1 over 1 plus x, where x is very, very small, is 1 minus x plus x squared minus x to power 3 plus so on. And believe it or not, I think Newton was the first guy to decompose this into Taylor series. How many things Newton discovered? Just amazing. Okay, so when we know how this term will end up looking, we can investigate hydrostatic equation using these decompositions. We write minus 1 over rho delta p delta z minus g is equal, so I am using this hydrostatic equation, minus 1 over rho naught plus rho prime delta delta z p naught plus p prime minus g. And that is approximately equal, now I will use this Taylor series decomposition, 1 over rho naught, 1 minus rho prime rho naught, I only keep first two terms, which multiplies delta p naught delta z plus delta p prime delta z and minus g. And that is further equal. Let's continue here. 1 over rho naught, here it should be minus, sorry. Rho prime rho naught minus 1. So I removed this minus, but I flipped the order. Delta p naught delta z plus delta p prime delta z minus g. And that is equal 1 over rho naught. This times this is rho prime over rho naught delta p naught delta z. I could also in principle use normal derivative, it doesn't matter because p naught is only function of height, it doesn't matter, plus this times this, rho prime rho naught delta p prime delta z, minus this times this, delta p naught delta z, and minus delta p prime delta z minus g. Now I hope you will notice that this cancels with this, because when I multiply with this 1 over rho, I will get here positive g, because here is negative, and this negative g will cancel. This is higher order term. It's very small. We are multiplying two small terms, namely product of dynamical variations, and that's higher order term, so we approximate it as 0. And then this becomes approximately equal, approximately because of this approximation, as 1 rho naught, rho prime, rho naught, delta p naught, delta z, minus delta p prime, delta z, and that is further equal minus, if I take minus in front of it, 1 over rho naught. What is delta p naught delta z divided by rho? That is negative g. So I will have here rho prime, and this over here is negative g. times g, and this negative ended up here, and plus, because I took minus in front of it, delta p prime delta z. And this is our result. So we have these two terms. At synoptic scales, these terms scale as follows. Minus 1 rho naught delta p prime delta z. So this second term scales as delta p rho naught times h, where you will remember delta p is vertical pressure fluctuation, but you will also remember that the order of magnitude is the same as horizontal pressure fluctuation, 10 to power 3 pascals in both cases, and h is the approximate depth of the troposphere. So this term scales as 10 to power minus 1 meter second square. This first term, which is negative rho prime rho naught times g, scales also as 10 to power minus 1 meter second squared. How did I conclude that? Well, we know from measurements that rho prime is about 1/100th of rho naught. And g is 10. So you can see that the scale of this term is 10 to power minus 1. And guys, this is extremely important result because it tells us that at synoptic scales, perturbation pressure fields are to very good approximation in hydrostatic equilibrium with density perturbation fields. They are the same order of magnitude, which means we can write that delta p prime delta z plus rho prime g equals 0, which is also hydrostatic approximation, but for deviations from mean values. Extremely important result. And also notice that the order of magnitude of these terms is large, they are larger than other terms in vertical momentum equations. In other words, these deviations are more important than some other terms in Navier-Stokes equations. Furthermore, perhaps you heard of term hydrostatic model in atmospheric sciences. And then consequently you also heard non-hydrostatic model in atmospheric sciences. Model which obeys this relationship is hydrostatic model. Whereas a model that uses the full vertical momentum equation, which would be this, is called non-hydrostatic model. This is hydrostatic model. This is non-hydrostatic model. Notice that in hydrostatic model, we don't have acceleration terms in the vertical direction, which means we don't know how vertical velocity evolves with time. But wait, you might say, does it mean then that we don't know anything about W if we adopt hydrostatic model? The answer is we can diagnose W from mass continuity equation or thermodynamic equation and some other methods too. So to conclude, in hydrostatic model, we cannot explicitly calculate the evolution of W, namely vertical accelerations, but we can diagnose it using some other methods such as mass continuity equation and thermodynamic approaches. So we conclude this video by noticing that at large scales in mid-latitudes, atmosphere is in hydrostatic equilibrium, even in terms of deviations of pressure and density from their respective base states. This is an important conclusion that perhaps might sound the same as the conclusion from the previous video, but it's not. It's not because in previous video we didn't say anything about horizontal pressure gradients and deviations of state variables from their base state. In this video we also introduced concept of decomposition of a field variable into base state and deviation from that base state, which is extremely useful concept in natural sciences and engineering, and we will use it a lot in the future. It is used beyond dynamical meteorology. It is used in boundary layer meteorology, analysis of turbulence, wind fluctuations, and so on. And lastly, now you properly understand the difference between hydrostatic model or models and non-hydrostatic models in numerical weather prediction, computational fluid dynamics, and atmospheric sciences in general. Until next video, goodbye.